Multiple announcements. One announcement, whoever brought the really good smelling rolls, I hate you. You're killing me right now. Okay, I've got to get through this lecture. Okay. Wow, those smell good. It must be like cinnamon roll morning. Announcement number 2, the exams are graded. We haven't averaged it yet, but they were pretty good. The average will probably be like high 70s or something. So the average grade, and your grades all be released hopefully later today. We're typing them in as fast as we can. We have to type them in one at a time. Yeah. Announcement number 3, the pledge problem will be out very soon. We've almost got it out. It's due the last day of class? No, when is the pledge problem due? I don't know. Oh, you always have a week. So if we get it out today, it's getting close to Thanksgiving. We'll figure it out, okay? But it's a pledge problem about fluids, okay? So fluids will be on the final, of course. Announcement number 4. If you signed up for 126 and are pre-med, this is proof that it will be important in your future life. Olivia took, I think she may have taken 101, 102. But the point is physics in the emergency room. It matters what kind of a battery you shove up your nose or other orifice. Okay. No, nothing? Okay. Orifice is plural of orifice, and, actually it isn't. Other orifices. Other announcements. I think that's pretty much it. Okay, I should probably not have social media up on the thing. God knows what could possibly go wrong. All right. Last time I had a string out and I was clotheslining you and all kinds of stuff, and I forgot I have lots of videos of this kind of stuff that would actually be better to look at. So last time we talked about things like this. We talked about waves on a string, right? So I have better views of it. When I was trying to let you see down the string, it looks something like this. You shake one end, and there goes the wave. Ooh, right? So if you shake something in time, you get a variation in space, right? That's what we talked about. Oh, who's that idiot here? And here's another one. This one's even better. Watch the pulse go. Here I want you to see that it doesn't just have to be a sinusoid. You can get any shape, in principle, can go down a string. It doesn't matter what the shape of the function is. Oh, that was fast. I'm sorry. Maybe there's a slow-mo. There's no slow-mo. It's fast. Okay. So we're going to look at a few examples like that because they're probably better than trying to watch them in real time. They're too fast in real time. Okay, so let's look at what we talked about mathematically here. All right, so we said the way we were describing that mathematically is we apply the laws of physics to a medium. If we apply the laws of physics to like a psychic medium, it wouldn't take long. But here by medium, we just mean an extended system that has some property that we're going to interpret, or we're going to perturb, and we're going to watch it go, and we got a wave equation. And this was just for enrichment. We don't expect you to derive a wave equation. We don't expect you to solve a wave equation. I just wanted you to understand that like the equation that makes the oscillator, that describes the oscillator, there's an equation that describes all waves. And they all follow a very similar differential equation. Just different physical systems put in different variables for the different medium. Right? For the string, it's a deflection of the string. For air, it's the pressure of the gas. And all these things end up following basically the same wave equation. So we did, in a teeny bit of detail, the stretched string. The first wave, it's always your first wave, right? You got this thing, a wall, and a string, and maybe it's got some wave on it, like that. The wave could be going left or right, just like you saw here, right? The wave can go down a string. The book does sort of all this with different approaches and things called history graphs. So if you're someone who watches this and says, what the hell was that, and reads the book, understand the book approach is sort of like way too detailed in my opinion. Okay, we don't need history graphs. This isn't like interdisciplinary or whatever. And then there's like a 3-page derivation on which way the wave goes. I'm going to show you that in a little less than 3 pages. And there's sort of a fake derivation of the wave equation in there. So the book gets really detailed. I'm just telling you what we need to know, okay? We can't turn this into my sophomore class. Okay, so the main thing to understand is you have a medium for now the stretched string. You have a wave equation, and there's multiple solutions to the wave equation and multiple types of solutions. So in this semester, in 125, all we care about is the traveling wave. Okay? Traveling wave. Next semester, we'll talk about standing waves. That's the other fundamental type. But right now, it's just traveling wave. Okay? That's how I meet people. I just go around campus. Hey. And where our solution to the traveling wave then was this. We called it d as a function of position and time. Right? So d was like the deflection of the wave, up. And x was position, along. And time is just time. Okay? So we said, oh, it's some a sine. And then we had these variables, kx minus omega t plus phi. So we're going to play with those more today and how to use them in problems and what they mean, but we did sort of define them last time. So this is a traveling wave because this describes a sinusoid moving in positive x. So by moving, we clearly mean it's a function of time. That's what moving means. Positive x direction. All right? And then we define these, and we'll talk about them more today, that k is a wave number. It's 2 pi over the wavelength. You might be more familiar with wavelength. And that omega, angular frequency, is 2 pi times the regular frequency in hertz. So this is like your high school things, F and lambda. Here's your college stuff, k and omega. I don't know. Graduate school, everything's imaginary and complex. Now let's think, why does this thing go to the right? Does it really move to the right? We have a negative sign in front of the time. Does that really make it move to the right? We can do it, so we're going to prove this by coding it. We're going to do programming now. Yay. Now let's see, we're going to do programming. Look at everybody's face. No one cares, okay. So if you're a computer science person, we're not really going to do programming. We're going to do MATLAB, okay? So it's not really coding. If you're pre-med, this is a different kind of coding. This is a program that's going to make a plane wave. Look, all we did was we defined k, and we said it's 0.2. And omega is 0.2. And here we're making an x-axis from 1 to 100 meters, say. And we're saying we're going to calculate the y at 100 times, right? And then we're going to make a movie. All right, we're making a movie. We're saying for time is 1 to 1,000 seconds. Let's write this equation. And here it is. Y equals 5. That must be the amplitude. Times sine of k. That must be the wave number. Times x minus omega times t. Right? So this thing is a function of x. X is like, 1 to 100. So it's calculating this shape, y of x, for all position for a certain time, and then plotting it, and then really plotting it right now. Draw it now. So if we plot that in real time, let's see what it does. Oh, it moves to the right. Look, there it goes, to the right. It's a sinusoid. Its amplitude is 5. It's moving to the right. Wow. Let's see, why is it really moving to the right? Let's do this. Let's plot it. Let's let phi equal 0. So it's really just a sine kx minus omega t, right? Oh, God, I got shit everywhere. And now let's plot it at t equals 0. So at t equals 0, it's just a sine kx. So I can draw a sinusoid. Watch this. Thank you. Sinusoid. Okay, what is its amplitude? Oh, it's a. It goes to plus a here. This is for people just catching up here. It goes to minus a there. That's the origin. Sinusoid. Ooh. More like that. There we go. And now that's at time equals 0. What if we let time go forward a little bit? Oh, I should do color chalk. No, never mind. T equals 1. Okay? Let's let time get bigger. What happens when time gets bigger, but say we want to find this place where the 0 is going to be. Where's the 0 going to be? If time is bigger, like t equals 1, but we want kx minus omega t to be 0, what does x have to do? X has to also get bigger, because the time is negative in there. Right? T gets bigger, like t equals 1. We want that to be 0. So x has to get bigger. So in the little part under the sign, because the time is negative, when it grows, this has to grow if we want to keep up with this point. So we go over here. Like that. So which way did it move? It moves to the right. A negative time constant here makes the graph move in positive x. Just accept it, okay? I'm trying to explain it a little bit. If you don't like to understand it, if you don't know what I'm talking about, just accept it. If there is a minus sign here, it moves in positive x, all right? Now, using your amazing powers of deduction, if I put a positive sign there, which way will it move? Negative x. Here we go. I can't believe we're doing this live. Oh my God. Look at that. It moves in negative x if I put a positive sign there. Dude, what if I put a multiplication in there? Oh man, this is going to be cool. How do I stop it? I've never done this before. Let's see what happens. Oh, dude, oh my God. I've made something amazing. Look at that. I have no idea what that is. Okay. Don't put a multiplication sign in there. That is not part of the class. That is just for fun. My idea of fun. Is the amplitude the same with bigger time? What? That doesn't make any sense. Is the amplitude the same with bigger time? No, in the wave we're describing, the amplitude is constant. We'll talk about the amplitude changing in a little bit. But yeah, A is a constant here. Okay, because there's no decay. Remember, for the damped oscillator, I'm layered here. For the damped oscillator, it went down in time. My God. But here we don't have any damping on these waves. They go forever. Okay. Okay. One page down. Here we go. 10 to go. So now we want to ask, so now we've confirmed, we understand the wave, we reviewed our topics here, now we know what's going on. So now we want to figure out how fast does it go, right? The wave goes really fast. How fast is it? Just want to turn that off. There we go. Yeah, so let's look at the wave speed now in more detail. Yeah. All right. God, no, Lord. Oh, that's stuck up there. Yes. How fast is this starting to look like being at the zoo? I don't know. Is the wave? The wave. How fast is the wave? Okay. So you just saw one flying by. You can see it moving here. So the quick way to get the speed in terms of what you know would be to say, well, I would say I'd do it like this. The speed is that it goes a full wavelength over a full period, right? That's how fast it's going, right? The whole sinusoidal pattern moves from here to here, and by definition, that takes a period. So if you know that wavelength and you know how long that takes, that's the speed. So the simplest formula for speed is that it's lambda, the wavelength, over t, the period. If you're really into frequency and not period, you can say that lambda is the frequency. I'm sorry, that the speed is frequency times lambda. Right? That's it. That's all there is to it. V equals frequency times wavelength. But you know that in sort of grown-up physics, we like to use radians. We like to use radians. So what we do is we take our V, we take our lambda over, let's take our lambda over period, and we multiply it by 2 pi over 2 pi. Can you do that? Yeah, right, because 2 pi over 2 pi is 1. So just multiply it by 1. We can also multiply it by 1, again. Okay, wow, look at that. And then you can look at it and start regrouping it and saying, oh, this lambda over 2 pi, we call that k. And then what is 2 pi over t? That's 2 pi radians over the period. That's omega. Right? So you can also say v. No, I'm sorry. Wait. What have I done here? This is 1. I'm sorry. Lambda. Yeah. Okay. Start over. K is 2 pi over lambda. This is 1 over k. Of course. Yeah. K is in the bottom. Right. And then 2 pi over t is of course omega. Yeah. Right. So the way physicists think of it is in terms of omega and k. V is omega over k. But this still isn't even how physicists think of it. Right? We rearrange it to make the most famous statement of the problem, which I'm going to look up because I've now screwed this up and thrown myself off. Omega is VK. Okay? So if you're solving problems and you don't really want to think in terms of radians, I would remember that V, the velocity, is the frequency times the wavelength. But if you go further in physics, you'll see this written down all the time. Omega is VK. It's the exact same thing. It's just one is in radians and one isn't. The way I really remember it is, how many people here are from Dallas? Yay, DFW, right? So when I was a kid, we called this W for the wavelength. And we said, oh, V equals FW. And I thought, oh, DFW. Right? So that's how I actually remember it. So that's why every time I teach and talk about physics ever, in my head I have to convert from DFW to omega equals VK. So that's why I screwed it up. I was thinking about Dallas. And I was from the wrong side of the tracks in Dallas, so, it takes me time to recover. Okay? Now this is sort of how the wave speed relates to the frequencies, the time frequency and the spatial frequency. But each wave medium, the wave speed itself depends on properties of the medium. Of the medium. Right? So if I gave you like a wave equation, and from it you could come up with omega and k, you could say, okay, I know the speed of the equation. And then you might mistakenly say, oh, it's determined by omega and k. But not really. That's just more how it relates to omega and k. It's really physically determined by how stringy, heavy, and pulley, and stretchy the medium is. Right? So for the string, it looks like this. The velocity is the square root of the tension over the mass density. I think we wrote that last time. Right, tension over mass density. So if you put everything in whatever, newtons per meter, coulomb squared, blah, 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 it'll come out in meters per second. If you put tensions in newtons and mass in kilograms per meter, it'll come out. Why do we have to wait until the middle of November for it to be warm in here? I don't know. I don't know. Let's see. I could prove this to you if we want. We could actually know the properties of that string. If we want, we could have a quick look and calculate it real fast. Let's see if we can do it right. We're going to do a demo through the magic of videotape here. So the typical string that I set up that you see, that stretchy string, has a mass density of 0.0039 kilograms per meter. So we're just going to take this little corner of the board and do the demo now. Mu equals 0.0039 kilograms per meter. This is for the string. Okay? Yeah, okay. And the tension we can actually set. So if I look at this thing, and the tension was set at 1.27 newtons. So for yourself, on your phone or whatever, be calculating what you think the velocity is going to be. That'll be fun times, right? The velocity, let's see, so the tension's 1.27 newtons. Right? So from that, we should be able to get the velocity. It's the square root of t over mu. So it equals blah, 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 number. It equals 18 meters per second. That's pretty fast, right? World-class 100-meter sprinter is going 10 meters per second. So that's twice as fast, almost. Okay? So now we're going to watch it at a few speeds, and we're going to see if we get the right answer, right? So here we go. So here's a pulse going by, very fast. It's in slow motion. 1/10th speed. Look at it go, very fast. Oh, I have the lights on. 1/50th speed. Look how fast it's going by. So it went through those marks in 3.33 seconds at 1/50th speed. It got from there to there. So let's see what we get. If we did this as a demo, we'd say, how fast did it go? Here to here is 1.2 meters. These are 30 centimeter marks. 34. So V is 1.2 meters in 3.33 seconds over 50, because it's 1/50th of a second, or it's slowed down by 50. What do you get? 1.2 divided by 3.33, that's a factor of 4, or 3 times 50, it's 1, you get 18. You get 18 meters per second. Okay? So if you measure all this and you run it, it's exactly right. Okay? So now you can look at it and say, so does this mean that this is the equation for the speed for every wave? It seems like if it worked so well for this wave, it should be the universal speed. And the answer is no, because remember, the wave speed depends on the properties of the medium. So if you calculated the wave speed for sound, you're doing it with like the ideal gas law, not tensions in a string, and you'd get something else. But it would still be, it's usually kind of like the square root of something that has to do with how stiff it is and something that has to do with how heavy it is. It's always kind of similar. But that equation is only for the string. This equation is for any wave. Okay? This is general mathematics of waves. This is physical. Okay? All right, so now you believe me. Okay, here we go. So now, this is all interesting. How can we possibly do homework on this? So now we'll do a homework problem on this. Here we go. I want to show you how to use this thing mathematically here. Let's see. What does mass density mean? Mass density is the mass per unit length of the string. So that's why it's in kilograms per meter. So I took that string, and I cut a meter, and I took it to my lab, and I put it on the scale, and I got the wrong number because it wasn't stretched yet. So I took the string and stretched it and said this much is a meter when it's stretched, and I took it and it unstretched, and I weighed it in my lab, and that's really a meter once it's stretched, and I took that mass over a meter, and that's what that is. So it's literally just a measured mass per unit length, but it changes when you stretch it, so it depends on the tension. So, okay, so let's do a wave example. Right, so in this example, you're just going to they're going to draw you a wave. Here's a wave where you're given the graph. It's a function of position. This we're just going to call y. We're not even saying it's a string. It's just something happens in the y. Maybe it's position, maybe it isn't. And we're going to draw it as a sine. Looks like a sine wave. And it's going to go up to 2. And let's go down to -2 and whatever x is, who knows. And this first thing is going to happen at 1.5 meters. And then this second thing crossing here is at 3 meters. At this instant in time. Right? Since there's a wave equation, this thing's actually flying to the right. So I think we're going to say, well, this is, say, t equals 0. Okay? So that's not quite everything you need to know about the wave. You need to know something about time. Right? You know nothing about time here. All you know is the shape at some time. So you know how fast it's going. We're also going to tell you that the whole thing is moving at 6 meters per second. So this is a test of do you understand how to use the equation and the real relationships. So over here, while you're thinking about that, somebody asking, why did you divide by 50? Because the video was slowed down by 50. So it was literally 3.33 seconds in a video that was slowed down by a factor of 50. So it was actually a lot shorter than 3.33 seconds. Yeah, it was for fun, really. Okay, so we want to write the equation. So here, A. Write the wave. It's really not the wave equation, it's the wave solution. The wave equation is that differential equation we wrote down last time. We want the solution, A sine kx minus omega t. Okay, so I would say, well, I would call it this. A is what? That's the first one you got to know is what is A? 2. Amplitude is 2. Okay, so we say, okay, y for all position and time, 2 is the amplitude. And then, do you want to use a sine or a cosine? Okay, everybody gets to vote. 1, 2, 3, sine. Let's use a sine because at time equals 0, it looks like a sine. And then we won't need a phase. If we describe this with a cosine, it's actually a cosine shifted. We don't want to deal with that. Let's use a sine. So 2 sine. What are we going to put in for, let's see, the next letter is k. K times x. What is k? K is 2 pi over lambda. What is lambda? Okay, that's like how long for a cycle? 3. So 2 pi over 3. And what do we put in for x? X. It's an independent variable, right? We've got to write the x. So k is a constant, and in this case, it's 2/3 pi. So you got that by reading the graph. All right, smarty pants. Now, which way is it going? to the right, which means the sign in front of the time term is negative. I could spend all 70 minutes on that point. And after the lecture, somebody will say, now why does it go to the right when there's a negative sign there? Right? So, I'm a little time on it, but it doesn't really matter. Somebody will ask. And it's okay. Please, I want you to ask, because then the story propagates. So we got to have some sort of omega here, but we don't know much about time. All we know is the speed. Well, the quick way is go to the physics version. Omega is vk. Right? So you can actually say omega is v. What is v? 6. And then you put in the k that you calculated before. You mean 2 pi over 3? Yes, 2 pi over 3. And you might say, well, how can I use the k in the time part? I don't understand. That's the whole point of how the wave works. The frequency and oscillation and the spatial oscillations are related. That's what the wave equation does. It relates the frequency oscillations in time to the oscillations in space by the velocity. So if you have need for omega and you don't know it, you can use k if you multiply it by the velocity. Right? So we use this same number here. And now what phase do we need? We need no phase. Because at time equals 0, it's a nice sinusoid. So we aren't going to get into phase calculations yet. We'll deal with phase more later. So that's it, right? We could simplify it. What does this become? It cancels to a 2. It becomes 4 pi, right? 2/3 pi x minus 4 pi t. Okay, well, I wrote that in my notes, so I'm obsessive about this. So 2/3 pi x minus 4 pi t. There you go. So that would be the answer to part A. Right? Now, let's do a little trickier. Ooh, now, how can I make this unpleasant? Now, let's switch boards here. No. B, let's get the force on a piece delta x, at x equals 1.5 meters, or whatever unit it is. It doesn't really matter. Didn't really get into units. And t equals 0. What does that even mean? How am I going to get the force? Right, so this is the hard part, right? You can plug in chug for part A, but part B, you got to really know what's going on. Okay. This test, do you really know what this equation means? That's what we're really finding out here. I fear what the answer may be. Okay. So we're going to look at the thing and say, okay, maybe, by saying force, I guess I implied it's a string. Okay, so for part B, let's say it's a string, and these are vertical displacements of the string. I forgot. This problem implies it's a string. So we want to know the force on a little piece right here, delta x, right, at 1.5 at time equals 0. What force is that feeling? Well, you could probably maybe use your intuition and get it right, but let's do it mathematically. What do we know that's possibly going to give us the force? Kx, there's no spring constant k. There's only tension T. Somebody asked, what's K stand for? K is the wave number. K is the wave number. I just erased it. K is the wave number 2 pi over lambda. It's over there. So what we're going to do is, okay, so what do we possibly, can we get anything about that little piece, delta x? What can we get about it? We know its position as a function of time. So we know its position as a function of time. Maybe we could get its velocity as a function of time. Let's see. So that y is the position. What's the velocity as a function of time? Take a derivative with respect to time. Right? Say, okay, can I do that? I don't know. Let's see, 2. And sine becomes cosine. And the argument stays the same. Minus 4 pi t. And then how do I take a derivative of cosine? I have to pull out the derivative of this with respect to time. Stick it right there. Minus 4 pi. Right? So there's the velocity with respect to time. That's how fast that little delta x guy is moving at all times. Or this is how fast everything's moving at all time. We could put 1.5 in here and see how fast he's moving. Or she. Delta x is gender neutral. But we want the force, so it must be acceleration, right? So if we get its acceleration and we know its mass, that's how we can get the force. So we take another derivative. Oh, and get the acceleration of the whole thing. Cosine becomes negative sine, negative 2, negative 4 pi. We're going to pull another 4 pi out because we took another derivative. Squared sine 2/3 pi x minus 4 pi t. Interesting. Notice how we keep pulling out this one and not this one. It's because it's a time derivative. We're not taking a spatial derivative, we're taking a time derivative. Interesting. So there's the acceleration as a function of time. Very nice. Why don't we go ahead and simplify it? The acceleration as a function of time, it looks like squared becomes positive minus 2, so this minus hangs around. 4 times 4 is 16, times 2 is 32. Minus 32 pi squared sine of 2/3 pi x minus 4 pi t. Okay. So that's the acceleration everywhere. But now we want the acceleration of delta x. Now, this is everywhere. But for the delta x in this problem, it's minus 32 pi squared sine 2/3 pi. Where is it? It's at 1.5. So now I don't have a negative extra negative sign. You have a negative extra sign. A negative extra sign, an extra negative sign. I don't have an extra negative sign. You have an extra negative sign. I hope after that display. I hope I don't have one because then it'll be embarrassing. Okay, so x, we just plug in x. What is a convenient version of 1.5? 3/2. I did that on accident. You're welcome. Okay. So 2/3 pi times 3/2. And then minus, and what is this one? We said at time equals 0. Okay. Now we are getting somewhere. So what is this whole expression? This is that whole. You got to be good at algebra and trig. Calculus doesn't really matter so much, except for taking the derivative. 0. Right? 2/3 3 sine of pi. What is the sine of pi? 0. So the negative doesn't actually matter. There you go. We're both right. Because this is going to be 0. So if that's 0, then what is the force? Well, if we want, we could put everything in. We could say, oh, well, it's mu that you forgot to give me times delta x times the acceleration. But it's 0 because the acceleration is 0. So it's 0. The force at that point is 0. Why do you have 2/3 s? There's a lot of 2/3 floating around in here. This is 2/3 pi because that's from way up there. So I'm not sure where you mean. Why do you have 2/3? There's not an s anywhere. So let's see. Physically, do we believe that the force is 0 on that thing right there? Yes. Because the person who is thinking of it as a spring is kind of correct. Basically, every little element of the string is kind of going in simple harmonic motion. And when something is in simple harmonic motion and it's at the neutral position, the force is 0. The kx is 0. Right? In a continuum like this, really every little element is feeling kind of like a spring force, but it's really from the difference of the two tensions along the string. Okay? What really happens, if we want to get deep down, do you want to get deep down for a second? What really happens is you have to think about how the tension is different. Like if I looked right here, here the tension is this way, here the tension is kind of that way. That slight difference in tension because of the curvature is what gives you a force. So you can see that here the tensions are perfectly symmetric. So that's why the force is 0 there, which is also why it accelerates at 0 there. You might say, wasn't the force 0 here? No. Here the tension is kind of that way and it's kind of that way. There it's getting pulled up. So there's a relationship between the curvature and the net force due to tension. But that's beyond what we're doing. It's just your question inspired me to tell you that. I meant, where did 3/2 come from? Sorry, 3/2 came from, it happened at 1.5 meters. 1.5 meters is 3/2. All right. Is mu delta x like mass? Yes. So F equals ma. Mass density, and the little delta x has some size. Okay. Since the wave propagates is the same relative point on the wave, stay feeling no force through time? No. Right. That's why I said at time equals 0. So later, when, where's my damn board? Later, when, that didn't work. Later, when that part of the wave is up here, later when this is down here, it feels a force. Right? So it is like an individual part. It's kind of going through simple harmonic motion. Okay? And we would have got that answer if we didn't put 0 there. Right? If this had a value, would this sign have come out as 0? Probably not. Unless the value was pi or 2 pi. See, this is a good problem. Learning lots of stuff. Could you use v equals square root of t over mu instead to get t and then use that for a force? You could, but you screw it up, so don't do that. So what is moving at 6 meters per second? The wave is moving at 6 meters per second. So remember my video of the wave traveling down? It's moving at 6 meters per second. Don't make me show you the video of me trying to outrun a wave. Okay, it's really embarrassing. Okay. So that's an example of using, if you can do that, then you understand that solution, right? If you can figure out what omega is, what k is, and go this far, right? This is a calculus-based problem now. So this you have to be able to do. And then this would be like the little part at the end that's really hard, right? We didn't have any middle ground there. We just did the easy part, the straightforward part, and the hard part. Oh my God. No wonder we're so tired. Okay, yeah, so let's stop and we'll keep going. Oh, perfect timing. All right, let's keep going. So now we're going to talk about things beyond one dimension. I stole a minute from you, but you get minutes from me all the time. 3D or not 3D? That is the question. All right, 3D or not 3D? We're going to talk about waves that are 3D, but are they 3D? It's hard to say. Okay. The string wave. Was it 3D or was it not 3D? The string wave is, maybe it's 2D. No, is 1D because it only varies in one dimension. Because it only varies in one spatial dimension. I mean spatial, right? It only varies in x along the string. I don't have dimension yet. I'm getting there. Right? String waves 1D, right? Now you could say, oh, but wait a minute. But it's a transverse displacement. Right? If you think about how it really works, this big D, the D of x and t, is really in another dimension. It's not along the string, is it? Right? Yes, I know. I'm trying to not. Yes. I'd be a horrible lawyer. No. It's not 1D. Okay, so this gets into the question of if you take some lesser course about waves, the first thing they're going to say, the first thing in your stupid book is, let's classify waves as transverse or longitudinal. Okay, that is the least interesting thing in waves in all of physics in the whole universe, is whether waves are transverse or longitudinal. Okay, it's always the first thing they bring up because it's easy to think about and it's easy to write homework about, and you don't have to do any math. And I hate it. Okay, so I'm sorry. So string waves are transverse. Okay, but it doesn't make them two-dimensional, is my point. They're still one-dimensional because when we wrote this equation, a sine kx minus omega t, we wrote it multiple times. It only depends on x. It doesn't depend on this transverse direction. That's just the disturbance. So mathematically, what makes a wave, what its dimension is really just how many spatial variables show up under the sign. So that's why we would say a string wave is one-dimensional, even though it's transverse. Blah, who cares? Okay, but now it's going to get more confusing. Okay, because we're going to look at waves that are sold as 3D, right? A plane wave. So this part of the class has like vocabulary to keep up with. What makes a plane wave, there's many kinds of plane wave. It's not just a certain thing, is that it travels uniformly along a René Descartesian axis. That's really technically what a plane wave is. It looks a lot like the string wave, doesn't it? How is it different? So the way it's different is, let's do an example. Let's do a sound wave that is a plane wave. right? All sound waves don't have to be plane waves. You can have sound waves that are plane waves or other kinds. You can have light waves that are plane waves or cylindrical waves. But let's just do an example of a sound wave that is a plane wave. It would look like this. Mathematically, you would have the pressure as a function of just x and t, one-dimensional, equals the pressure amplitude times the sine of kx minus omega t plus some phase constant. We'll worry about that later. So you say, well, that looks pretty freaking familiar here, right? A is constant amplitude here. P naught's a constant amplitude there. Kx omega t phi naught. So what makes this a 3D wave? Or is it a 3D wave? That's why it's a question. Okay? So let's think about it here. Let's draw this mathematically here. So here we have somebody making a sound, right? So this is Kesha from the last lecture. She's got some weird eye makeup going on. Kesha. Right? And so she's making a sound like this. Oh, wait, she got rid of the dollar sign. I'm sorry. She got rid of the dollar sign. It's just Kesha. There we go. Actually, I think we should go with the cent sign, considering she got sued. So I would call her Kesha. I love Kesha. I'm sorry. I just, so much usefulness out of one person. Right? So this is x. And what is this? So the point is the plane wave, P doesn't have a direction in space, is it? It's a scalar. It's not a vector. So it's not like a displacement in a direction. You don't have to say, wait, is the displacement in y or is the displacement in z? No, it's just a pressure. So what you would say is everything along this plane that's riding along with this peak has high pressure. And then everything riding along here with this peak is like a plane with low pressure. All right? And then when you get back up to here, the pressure is 0. Or actually, for a sound wave, it's atmospheric pressure. You go above and below atmospheric pressure. But as you're going up high and you're going down low, basically, what the key is for a plane wave is that the value is constant along a YZ plane. For this example, right? We have it moving in x, so this would be y, and that's z. So in any YZ plane, it has the same pressure. Not all the time. At an instant in time, this is high pressure, this plane, and then this plane is low pressure. But if you wait half a cycle, this will be high pressure, and this will be low pressure for a whole plane. Okay, so in that sense, it is 3D. It's more 3D more than the string wave is. It's not that the physical thing is happening in multiple dimensions. It's just that it's constant over this plane. Right, so let's have a quick look. I can show you maybe a slightly more clear illustration of what a plane wave looks like here. I got one more to show you from back when I cared and did lots of animations for sophomore physics when I was only 35. Let's see. So here we go. Right, so there's the plane. This wave is going to propagate along z instead of x. This deal, right? And as it moves forward, it would get to this point, say, and all the arrows would be up. Oh, no, it's going to be off. And then down. Oh, the animations don't work. Oh, never mind. Okay. It was beautiful. Trust me. Go read my course reviews from 12 years ago. It was amazing. Okay. They changed the aspect ratio of, like, screens now, and none of the animations work anymore. Okay, so it's you people in your wide views' fault. It's this. Let's do something else. Okay. So hopefully you're able to visualize that without the animation, right? So you get the idea is this thing goes along, the pressure, is constant over a plane. That's the idea of a plane wave. We're going to talk more about this stuff. That'll make more sense. Okay. What other brilliant thing's going to do for you here? I don't know what that is. So now we're going to look at a second kind. That's a plane wave. That's a spatial sort of a wave. Planes moving along. They get from here to here. Maybe your ear is here. Right? Let's now look at type number 2, a spherical wave. So this will be a little bit different. It's not just like the plane wave. So it propagates in all directions from a point. All right, so the key words here are all directions from a point for a spherical wave. The key word for the plane wave that I underlined was along an axis. All right, so that one just goes along one axis. This goes everywhere. So the best example is like a light bulb, like that. This is what light bulbs used to look like. Here you go. There's a filament light bulb. So the way you would think about that is light goes this way and this way and this way in all directions, all radial directions, and the origin is here where the filament is. So they're often represented just by drawing circles like this, evenly spaced circles like that. They're very hard to draw in 2D. They're very hard to draw in 3D. Actually, a vector 3D wave is, a vector spherical wave is difficult. But what happens is you would say, well, okay, if I were going to plot it now in space, I'd say this is kind of like the maximum here, and maybe this is the minimum, and this is the maximum, and this is the minimum like that, where this is the radial direction. But of course, in spherical coordinates, anywhere from the origin is the radial direction. So you could also say it's going to look like this, and come down to there, and go up to there, and come down to there, and go like that. Radial direction. The same thing in every radial direction happens. Right? That's all it is. So let's look at our example. Is light. A light bulb, not quite a point source, but close enough. Now let's write down what the solution to the wave equation looks like. Right? We had string. You're good at that. We had plane wave. Looks just like string. You just have to realize we're talking about a physical extent rather than a string. But now this one's going to look different. Light is an oscillation of the electric field. So that's why I'm writing E. We want to know what's the electric field everywhere in space. But since we're doing spherical, we just need R. We don't need X, Y, and Z. We just need R because we're assuming things are spherically symmetric. Right? All that matters is how far out you go. The angles going this way and that way don't matter. Okay? So it equals some amplitude, but that amplitude depends on R now. That's what's special about the spherical wave. One, it's spherical, and two, its amplitude is not constant. Okay? Sine, and the rest is basically the same, kr minus omega t plus phase, phi naught. Right? So the main interesting parts is that the amplitude decreases, you can see here, and that it along all r here, right? Kr, not just kx, not just ky, not just kz, but along all kr. Okay? Goes in all directions. Now, the next two things I'm going to tell you, we will make up little problems about for this class, but really they're critical to understand for 126. So you're all taking 126. Who in here is not taking 126? Admit it. Oh my God. Why on earth would you only take 125? This is the boring one. 126 is the exciting one. I don't know what these PAAs are telling people. I don't know. So let's say real waves are in between. There is no wave that is a perfect plane wave. A perfect plane wave has infinite energy because it has a constant amplitude over an infinite plane, and there's no wave with infinite energy. There's also pretty much no perfect spherical wave. Nothing is perfectly spherically symmetric like that. Why is the amp decreasing? To conserve energy. So it's beyond what we could say now, but when we get into amplitudes Tuesday, we could talk about it. But the energy in this wave is basically the amplitude times the area, the surface area of that sphere. So as this thing moves out, that surface area gets bigger. And then the energy then of the wave of each wavefront would be increasing as it gets bigger. So the only way you can conserve energy is as the area of the wavefront gets bigger, the amplitude has to get smaller. That's the short version of the answer. So we'll address it a little bit, I think, Tuesday when we do intensities. I'm making this up as I go along. Okay. Do I really look like a guy with a plan? No, I don't think I do. Is the final cumulative? No. Or yes, we haven't decided. Do I look like a guy with a plan? No. We don't know. Okay, so real waves are in between. So let's have, Kesha's back. Oh, I'm going to get sued by Kesha. Spider eye. Okay. So what does the thing coming out really look like? Like when I'm talking at you, It's not a plane wave. If it were a plane wave, just a piece of a plane wave, only like you would hear me, right? And it wouldn't go anywhere else. It's clearly going out like this. But it's not quite a spherical wave, because if I get this way, you can't really hear me anymore. See how much louder it is when I'm this way, than when I'm this way, you can hardly hear, right? That's because it's not really going behind me as much. It's kind of barely going behind me. So really, if we had to plot it, it's sort of like a cone wave. It's like sort of a piece of spherical. Now in homework, we'll say assume it's a spherical wave or something, but there's a reason I'm showing you this. So you would say right along this line from Kesha's mouth to my ear in the front row, right? Looks something like that, okay? So we've got a thing, and it's technically the amplitude. Well, I don't know what's going on, sorry. Anyway, a wave goes that way, right? And then you get some going this way, but not as strong, right? Some going this way, but not as strong, like that. And then really weak that way, and really weak that way. Now, you still hear somebody behind, because it's bouncing off walls and all kinds of, echoes are everywhere. Okay, so you could think of it as kind of a partial spherical wave, okay? But what I want you to see is we could draw sort of what's called the wave front curvature, like this. It's sort of saying, let's draw all of the amplitude maxima and draw a line connecting them all. Right? So there's the maxima. I didn't draw these to have a nice, even, uniform, whatever, sorry. But there's the minima. Right? So you get the idea. So what is this curvature doing as I get farther and farther away? Right? It looks like a plane wave. Right? So far away, spherical looks like plane. And we use this all the time in the kind of problems you're going to do next semester, this conversion from spherical to plane. Okay? Now, that kind of sounds like a convenient thing to say. Is there any math behind this? Am I making this up? Sort of the math is you keep up with this radius of curvature, which is really just how far away you are. And what really matters? If my ear were really big, like bigger than it is, right, eventually this thing would curve. But all that really matters is your ear canal. I had to look up what to call that. I was like, what do you call the hole in your ear? I wanted to say something classy. Ear canal, okay? So as long as the ear canal, which is a few millimeters, is small compared to the distance to Kesha, which is like meters, tens of meters, couldn't afford the tickets, right? Then it's going to be a plane wave because it's going to have no curvature. But then another thing matters is that the intensity is dropping off as you go farther away, right? So you also need the extent, the length of your ear canal to be short compared to the length scale over which it drops off, which is related to the wavelength, right? So wavelengths of typical audio frequencies are sort of, meters, on the order of meters. So your teeny little ear canal doesn't care, right? So for sound waves, your ear cannot possibly hear anything other than a plane wave. It thinks everything is a plane wave, right? The plane wave hits your ear, and then all the magic happens inside your ear, okay? Let's see. Latest questions. More phase to talk about. One's about E field. I don't want to go that far back. Ask me after class about the E field. Okay, so one thing I want you to be able to think about is you move far enough away from a spherical wave, it becomes a plane wave. All right? And then the other thing we got to understand for next semester and this semester, we'll do some problems on it this semester, but really this will become critical next semester when we do interference and stuff, is we finally have to talk about what's going on with the phase, right? Phase is the hard part of waves, and I can prove it to you with science fiction. Phase constant, and then phase difference. These are three different things, okay? So anytime you watch science fiction and they want to need something magic to happen, but they want to justify it with a little bit of sciencey sounding words, what word do they always use? One. The word one. Okay, sometimes they use the number one. Quantum, yes. And what comes after quantum? Phase, right? They don't ever say in terms of amplitude or radius, because you're going to know they're bullshitting you. Like, I know what amplitude is. You can't be here and then suddenly be over there because you changed your amplitude. Give me a break. But if you say phase, oh yeah, well maybe. And that's because nobody understands what phase is, okay? So let's talk about the three kinds of phase, okay? So let's go back to the string because it made sense, I guess, right? A sine kx minus omega t plus this phi naught. And I should have been putting a knot on it every time. I may not have been. Thank you. Okay. Okay, here we go. So the three differences, right? The entire argument under the sign, or the argument of the sign, is the phase, okay? So one big misconception is that this is the phase. This is the phase constant. The whole thing is the phase. Because phase just means where you are on a sinusoid, or how much you change your position on a sinusoid. Am I at the positive maximum? Am I at the negative maximum? Am I at the zero? Am I halfway? That's going to depend on all these things, right? On the wave, it depends on where you are and when you are and what your initial phase was. Okay, so phase, whole thing. Okay, this phi naught is the phase constant. Okay, so say you want to adjust where zero is, or you want to have some, say you know, like if you have a certain k and a certain omega of a wave and you work it out and it's not in the right place at the right time, but all you need is to adjust it a little bit, you put in a phase constant. You put in a constant number there, and that lets you adjust it. We're not really going to calculate these, I don't think, this semester in this class, but it'll come up next semester. So I just want you to know what it is. Just a constant that doesn't depend on time or space. Okay. The third one, yeah. So technically, that we could write this one also this way, is the absolute phase. The phase without the phi is kx minus omega t plus phi naught. Just to make it clear, it's the whole thing. Okay, so now the important part is we've got to talk about the phase difference. Okay, this is the thing that you use to calculate lots of properties, is phase difference. So I think your book blows through phase really fast, but I think we need to spend time on it because next semester it'll be so important. Next semester will make a lot more sense if we think about this now. So you're going to get it in your head, you're going to noodle on it with your subconscious. Let's see, now phase difference. Phase difference, we're going to call it delta phi. So we should always use phi, phi naught, and delta phi. Sometimes we slip up. So if it's a difference, it clearly means between 2 points. Right? Okay, so let's see. What is the phase between 2 points? Let's imagine here, here we go, that we have an xy coordinate system. You're good at that. Right? Y here, x here, origin, whatever. Okay, origin. It does actually matter. And let's say you have a point source here. Point source, what does that mean? Oh, spherical waves, right? When you hear point source, you should think, spherical waves. But my ear is small. Maybe it won't matter. Let's find out. Right? Point source there. And we're going to think about from the point source, which is at a position, x, what's happening at the origin and what's happening at a position p, which is at a height y. We can just call it y. Right? Okay, so source at x comma 0, it's x0, right? So no height, just no y. Point p at y, at 0 comma y. Right? I'm just telling you where these things are located. The origin is at 0 comma 0, as usual. So I think the way I wanted to say it is, what's the phase difference to the origin? Would be an awkward way to say it. This is crappy chalk. What is the phase difference from the source to the origin? See what I mean by that? The source is at x0, that's that. Okay? So the way you calculate a phase difference, if you're just dealing with spatial things, is you call that the path difference. So usually you'd write it like delta phi, that's what we call these, and then you can put a subscript to think about what's causing this phase difference. So right now we're just thinking about paths. Right? You could imagine that paths might screw it up, difference in time might screw it up, difference in phi naught, reflections can do things. None of that right now. Let's just think in terms of path. Let's see. So how are we going to get that? Well, it's really a question of how many cycles does it go through? Well, how long? Well, first of all, how far does it go? It goes x. Right? So delta path, it's definitely going to depend on how far it goes. D, we'll call it D to be general. Okay? How far does it go? And then over lambda, how many cycles? And then in terms of radians, everything's in radians, we have to have a 2 pi. Right? That's the number of cycles. Each cycle is 2 pi. So that's awkwardly written. It's supposed to be 2 pi d over lambda. Should have done the 2 pi first. Okay? So in this problem, we would say, well, it's easy. It's just it went from how far did it go d. It's 2 pi. And we would say, how far did it go? X minus 0. It just went x. The wave went that far. X minus 0. Over the wavelength. Lambda. Right? So that's the phase difference from the source to 0. What about the phase difference from the source to point P, to this place? So that would be from source to, I called it P. So we just look at it again. We say, okay, delta path, delta phi path equals, what's the distance? No, it's not y. It's a square root of x squared plus y squared, right? It's like a triangle. So it'd be 2 times pi times the square root of x squared plus y squared over lambda. Right? So there we've calculated how many cycles it goes through at 2 places. What's the phase difference from the source to the source? 0. Right? What's the phase difference when you go from the source and you move 1 wavelength over? 2 pi. Right? You move 1 wavelength over, that's d is lambda. Lambda over lambda is 2 pi. So the reason these are important is later in the next semester, we're going to think about having 2 sources come together. Right here I had 1 source illuminating 2 places, but you could also have 2 sources illuminate 1 place. And then you think about what happens when 2 waves overlap. And that's why we've got to be good at calculating these phase effects. Okay? For this semester, all we do is say, what does phase mean? Can we get the difference in phase? Okay? So then the last thing is really just vocab for like sound and light that you just kind of need. It sounds painful to start something now, but literally it's 2 minutes. Let's just have 1 board of sound and light properties because it helps you do the homework if you know a little bit about what sound and light are. Let's see. Okay, real quick. And I've sort of said them a few times already. I just want to throw some numbers your way. Okay? Here we go. Sound. I've said multiple times, there's a pressure wave in air. The only subtlety left is that it is not around 0. On Mars, it might be close to 0, but here, it's around atmospheric pressure. And la 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 like that. And this is position, and it's going this way in time. And how fast is it going? Oh, we'd have to apply the laws of physics to the gas law equation and do a bunch of calculations and have continuity in there, and we would get that it's 343 meters per second. So that's fast. It's not like ridiculously fast, but it's kind of fast. So up here we have pressurized air, and here we have rarefactorized air. Right? So we lower the pressure above and below atmospheric pressure. When you go into a solid, it goes higher. So V, for water, you'll probably need this for some homework problems. And since some of you don't have the book, there's a number for you. And maybe you don't have the internet also. And then also here, that's in water. And then here, it's at like 6,000 meters per second for metal. So just to give you a little intuition, sound speeds up a lot when you have a condensed piece of material. Right? In gas, molecules are missing and pushing on each other in the gas phase. They're really far apart. But in a solid, they're right next to each other. And when one moves, it pushes the other one really quickly. Okay? We hear, also to build your intuition, 20 hertz to 20 kilohertz. Depending on age, right, and other medical conditions, it might be different. You can probably hear higher than I can, although there's a fun demo when you turn it up higher and higher, and people still claim they can hear it, and then you show them you unplugged it like 5 minutes ago. So I should have done that to you, but we ran out of time. You can also, and then sort of the wavelengths here, you can also go ultrasound. Right? That's this thing that can see through your body by how sound reflects back, which is velocimetry, which we're going to talk about, I think, Tuesday. And that's hundreds of kilohertz, so higher, ultra meaning faster, to megahertz. But then we could say, well, what's the wavelength? The wavelength kind of tells you what kind of imaging resolution you could get from an ultrasound. So I could say, what's the wavelength in an ultrasound if you're at 3 megahertz? Would be a question. So maybe you could do it lambda at 3 megahertz. You'd say, oh, I'm from Dallas, V equals FW, F lambda. And you'd say, what V would you use? Water. Are you most like air, water, or metal? I am totally metal, but you guys are mostly water. So 1480 is frequency, 3 megahertz. And you get that lambda is like a half a millimeter. Right? This is why you don't get sharp detail of your little nephew that's coming along or whatever ultrasound picture you've been looking at. Okay. Oh, I'm going to do light off the top of my head. I'll save light for next time. We don't have to do light. Light is really fast. Okay, that's the main thing to know. Okay.